Hello and welcome. We are going to wrap up this unit on limits by talking about what happens when a limit results in infinity or when a limit is tending towards infinity, and what happens if we take the limit as x approaches positive or negative infinity. We're going to look at some techniques for simplifying these types of limits and work through some examples. So let's start with limits at infinity. If I look at the limit as x approaches positive or negative infinity, this is called a limit at infinity because we're taking the limit as we go to infinity. And this actually goes back to an Algebra 2 concept, really focusing about end behavior. What is the function doing, or how is the function behaving as x goes toward infinity or toward negative infinity? If that limit is equal to a number, then we say that that limit exists. So as x goes to infinity, if the limit of f, or if the function is tending towards 5, then we would say that limit is 5. If that limit goes towards positive or negative infinity, we would say that that limit does not exist. But now, if it is tending toward one of those, we could actually say that that limit is infinite, or it is negative infinity. So infinity or negative infinity are still limits that do not exist, but they're describing how they don't exist or how they are behaving, which enables us to really analyze the function on a deeper level. So you can still say that the limit doesn't exist, but more specifically saying that that limit is infinite, if that is in fact the case, is going to be more descriptive and more helpful when we move on to future topics. A couple reminders about asymptotes, since those impact and are often the cause of us having a situation like this. If we have a function like 2 over x minus 5, as we have been talking about, even just with continuity, we would say that this has a vertical asymptote at x equals 5. And as we look at later in this lesson, you're going to see how having a vertical asymptote could mean that the function is approaching the same infinity, or it could mean that it is approaching opposite infinities. So we can think about one-sided limits and potentially two-sided limits as well, but I'm jumping ahead of myself. One of the ways that we think about horizontal asymptotes is when we think of functions that have rational expressions that have the same degree. So if I had x squared plus 2 over x squared minus x, actually let's make this 2x squared minus x, we would divide the leading coefficients to identify that this has a horizontal asymptote at x equals 1, at y equals, since it's horizontal, 1/2. So those are things that we're keeping in mind when we're analyzing these situations. And let's actually look at some more examples of what goes on when we have rational expressions, when we have a polynomial in the numerator and the denominator. So we can use the fact that the limit as x approaches infinity or negative infinity of a constant over a rational expression is equal to 0. This is a fact that you can use. The reason being here is that the top is staying the same and the bottom is growing towards infinity. And if I have something constant over infinity, this is really just going to 0, tending towards 0. So what happens if we don't have a constant in the numerator? What happens if the degree of the numerator is greater than the degree of the denominator? And let's just go really basic here and talk about, well, what's happening if we have x to the third over x, if we have the limit as x approaches infinity of this? In a different video, I actually walk through sort of a factoring out method that you can use on problems like these, but for right now, I really just want to focus on the behavior of the function. So if the numerator is x to the third and the denominator is x, and let's make this x plus 1 so that I couldn't just simplify this. In terms of the dominant behavior, what's driving the behavior of the function? Well, the numerator being x to the third is driving the behavior of the function, and the denominator being x is driving the behavior of the denominator. So I'm asking myself, which of those is growing faster? This is really like thinking about the limit as x approaches infinity of x cubed over x. And that actually could simplify the limit as x approaches infinity of just x squared. And what's happening here, this is going to infinity as I plug in larger and larger and larger numbers. So if the degree of the numerator is greater than the degree of the denominator, we say that that limit is tending towards positive or negative infinity, depending on what is being plugged in. And the way you can think about this is that we can just say that what's happening in the numerator is fast and what's happening in the denominator is slow. And since the faster part is in the numerator, that's going towards infinity. Now, if the opposite is true, if the degree of the denominator is less than the degree of the numerator, so the limit as x approaches infinity of, let's say, x plus 1 over x cubed, this limit is now, the top is the slow part and the bottom is the fast part. And what's happening, the bottom is growing really, really fast and the top is growing much slower. So this is tending towards 0 because for the same logic that we looked at up here, the bottom is growing so fast in comparison to the top that the top is almost not even relevant. You could also think of this as the limit as x approaches infinity of x over x to the third, or the limit as x approaches infinity of 1 over x squared, and that gets us back up to this situation here. So even though these functions aren't the same, the limit, the way that they're behaving at the end of the function, is the same, so you can think about it in that way. So degree of the numerator greater than the degree of the denominator, this limit is going to 0. And then what happens if they are the same? If the degrees of the numerator and the denominator are the same, then you would just divide the coefficients. So let's say we had the limit as x approaches infinity of 2x squared over x squared plus 1. As we were just saying, behaviorally, the limit is going to be the same as if I took away that plus 1. Well, now the x squareds are going to divide out, and this limit would just be equal to 2. So if they are the same, you're just going to divide the leading coefficients. So keep these three scenarios in mind when you have a rational expression. Is the degree of the numerator greater than the degree of the denominator? If so, is that tending towards infinity or negative infinity? Is the degree of the denominator less than the degree, is the degree of the numerator less than the degree of the denominator? That's tending towards 0. Are they the same? Then divide the leading coefficients, just like you would define the horizontal asymptotes. Let's look through some examples. All right, so for this first example here, we have two polynomials. So this limit, and let's pick one infinity. Let's just look at positive infinity, even though this is going to be true for both. The limit as x approaches infinity of x squared plus x to the fifth plus 2x squared minus x over 3x to the fifth minus x to the third plus 1. So yes, there are other things happening, but again, we care about the dominant behavior. This is the dominant behavior. Those degrees are the same, so we're going to divide the leading coefficients. This limit is going to be equal to 1 over 3, since there's an invisible 1 here, and 3 is the leading coefficient in the denominator. For the second one, notice that with this square root, no matter what comes out, it's going to have to be a positive number. And what's happening here behaviorally, the dominant part of the numerator is this square root of 9x squared. And the square root of 9x squared is just 3x. And this is going to infinity. The top is changing, even without writing it this way. The top is fast. The bottom is constant. I wouldn't even say it's slow. It's constant. Fast over constant is going to lead us to a limit of infinity. Something to notice is that for this first example, there would be a horizontal asymptote at y equals 1/3, which makes sense that that is the limit that this function is approaching. You could go ahead and open Desmos and graph it and see that for yourself. This second problem doesn't have a horizontal asymptote because what's happening is that it's growing to infinity. It's not growing towards one number, it's growing towards infinity. Let's look at some more examples. The directions here say determine if the limit exists. If so, state the horizontal asymptotes of the function. So here on number 1, what's happening is that we have a constant over something that's tending towards infinity, so something that's moving fast. This limit is going to be equal to 0. For number 2, looking at this polynomial, we're going to look at the degrees. So we have 2 to the 5th over 2 to the 4th, which means the degree of the numerator is moving faster than the degree of the denominator, which is moving slower. 5 and 4 are our exponents there. Now I want you to notice that this is as x approaches negative infinity. So what's happening in the numerator, if I'm putting something negative to the power of 5, I'm getting a negative number. And what's happening in the denominator, I'm getting a positive number. And which is moving faster than numerator. So this is tending towards negative infinity. Negative because that's what's happening dominantly, or that's what's happening x to the 5th over x to the 4th. And then towards infinity because the degree of the numerator is greater than the degree of the denominator. Number 3, the degree here is the same, and to the 6th power, doesn't matter if we're going towards plus or minus infinity. What's happening here is that we're just going towards 14 over 3, since the degree of the numerator and the denominator are the same. There is also a horizontal asymptote at y equals 14 over 3. All right, I encourage you to pause the video and work through 4, 5, and 6 on your own. So hopefully you have taken some time to work through these examples, and let's look at them together. So for number 4, thinking about the degree of the numerator, I'm not going to expand everything out, but I'm going to think about what would happen if I did expand everything out, negative infinity. So this, if I expanded this out, would become x squared plus 2x plus 1, but it would become x squared. That's the leading term. And I'm going to multiply x squared by 2x. So that's going to give me 2x to the 3rd. Again, I'm not saying that this is equivalent. I'm saying that it has the same limit, or it's behaving in the same way in the numerator. This is over 5x to the 3rd power. That's the dominant of what's happening in the denominator. So they are changing at the same rate since they are both x to the 3rd, which means this limit is going to be equal to 2 over 5. Now, since both of these are 3's, even though I'm going to negative infinity, I'm going to negative infinity in both the numerator and the denominator. So a negative divided by a negative would give me positive 2/5. On number 5, the degree of the numerator is moving slower than the degree of the denominator, which means that this limit is going to be equal to 0. And then the last one in this section, the limit as x goes to infinity of sine of x over x. Well, the denominator is moving incredibly fast, and the numerator is basically going back and forth between -1 and 1. And even though it's oscillating back and forth, that oscillation is irrelevant with how quickly the denominator is growing. So this limit is going to be equal to 0. Now that we've worked through some limits as we go to infinity, let's talk about what's happening when our limit actually is approaching infinity. Not as x approaches infinity, but the value of the limit is approaching infinity. So in previous sections, we've already talked about limits that don't exist because of a vertical asymptote, an oscillation, a jump, discontinuity. But what we're going to talk about now is that we can describe the way in which some of those limits do not exist. And that is true if we're either talking about the one-sided limit or if we are talking about a limit in which both the left-hand side and the right-hand side are approaching the same infinity. Now that limit still does not exist, but a more specific way to describe how it doesn't exist is to say that that limit approaches infinity or approaches negative infinity. Now, if the limits aren't doing the same thing, if one of them is going to positive infinity and the other is going to negative infinity, we're still just going to say that the limit as a whole does not exist. So when we're thinking through these next 3 problems, we really want to think about what is happening on the left, what's happening on the right, and are those two things the same? And when we're thinking about what's happening on the left and the right, it's okay for us to pretend to substitute in a number a little bit to the left or a little bit to the right. So let's see what we're talking about here. Number 1, this function, 1 over x to the 3rd, has a vertical asymptote when x is equal to 3. Because it has that vertical asymptote, what I want to know now is, are the behaviors on both sides of this the same? So what I want to think about is the limit as x approaches 3 from the left of 1 over x minus 3. And the limit as x approaches 3 from the right of 1 over x minus 3. If those two limits are tending towards the same infinity, then the limit, we can say, even though it doesn't exist, we can say that that limit is tending towards positive or negative infinity. So if I'm thinking about from the left, in my head, I'm just going to pretend to plug in a number a little bit less than 3. So 2.9, 1 over 2.9 minus 3, that's going to be negative. So on the left-hand side, this graph is going towards negative infinity. On the right-hand side, if I pick something slightly bigger than 3, like 3.1, 1 over 3.1 minus 3, that's going to be tending towards positive infinity. So one side of the limit is going down forever, the other side of the limit is going up forever, so we will just say that this limit does not exist. If they were both going towards the same infinity, then we would say that the limit exists. Okay, let's look at number 2. We have a vertical asymptote when x is equal to -2, which is the value we're taking the limit of. So because we can't substitute this in, let's think about this from both sides. The limit as x approaches 2 from the left of 3 over x plus 2 quantity squared. Well, if I plug in something slightly to the left of -2, like -2.1, this part is going to be negative, but then I'm going to square it and it's going to be positive. And that limit is going to become 3. So this is tending towards positive infinity. In the denominator, we're tending towards positive infinity. Now if we think about, I don't want that equal sign to be there. This is not equal to. Then if we think about the limit as x approaches 2 from the -2 from the right of 3 over x plus 2 quantity squared. If I plug in something slightly to the right, this is also tending towards positive, right? Because I'm squaring that thing in the denominator, we are going to be going towards positive infinity. So we can say that the limit as x approaches -2 of 3 over x plus 2 quantity squared, that this limit is equal to infinity. Now it still doesn't exist, but by saying that it equals infinity, we're explaining the behavior that you would expect to see as we approach -2. So it's more specific, which is helpful. I encourage you to pause the video and work through number 3 on your own. So the first thing I did was simplify by factoring in the denominator. I noticed that there's a whole when x equals 3, which is okay. We're not considering x equals 3. But I rewrote this function so that it's a little easier for me to analyze it. So if I'm looking at -1, I do still have a vertical asymptote there, so I do still have an issue. So again, I'm going to think about what happens as I approach -1 from the left and from the right. I apologize for the sloppiness. My pen is not working very well right now. But if I approach from the left, so if I plug in something slightly smaller than -1, x plus 3 is going to be positive. Something smaller than -1 plus 1 is going to be negative. Positive times negative. This first limit is going to give me something negative. If I plug in something slightly larger than slightly larger than -1, this is going to be positive and this is going to be positive. And when I multiply two positive numbers, I get a positive. So this limit does not exist. It is not tending towards the same infinity. So let's recap what we've learned in this lesson. We first reviewed a little bit about horizontal and vertical asymptotes and the fact that when we're taking the limit as x approaches positive or negative infinity, what we're really doing is thinking about the end behavior of a function. We talked about how if we have a polynomial, how to analyze the degree of the numerator versus denominator to help us come up with what's going on. We identified those vertical and horizontal asymptotes. Then we talked about limits as we go to infinity, or as the limit goes to infinity because of a vertical asymptote or something else going on in the graph. And we talked about how you can describe a limit that does not exist using positive or negative infinity if both the left and the right side are going towards the same infinity. So go ahead and write down any questions you have or post them on the video below, and I look forward to supporting you on this. Thanks for listening.